Hi everyone. Okay, so today we're going to learn the derivative of the natural logarithm. So our learning goal is to find the derivative of functions of the form y equals ln, so that's how you say that, like your front lawn, of g at x, and ln stands for natural logarithm of, and it stands for, so this is y equals log to the base e of g at x. But because it's used so often in calculus, log to the base e, we call the natural logarithm. So when you see ln, it means log to the base e of g at x, of some function of x. So first of all, if the diagram on the side here, the one in red is y equals e to the x, which we talked about last time. And the inverse of a function we know is its reflection in the line y equals x. So if we were to fold that in half along the line y equals x, we would get the inverse of y equals e to the x. And you know from inverse from grade 11 and probably from advanced functions as well, as the inverse is you switch the meaning of x and y. So instead of y equals e to the x, we have x equals e to the y. And then we also know that we can write an exponential. So I'm going to start off with, for instance, 5 to the third, there's something in exponential form equals 125. And we know we can write that in logarithmic form. So this is exponential form. So this is a refresher from advanced functions. And logarithmic form. So in exponential form, this is the base, 5. 3 is the exponent. And 125 we'll call the value. So we can change that so it's in logarithmic form, and we would say that 3 is log to the base 5, so the base 5 of 125. Okay, so log to the base 5 of 125 is 3, is the logarithmic version of saying that 5 to the power of 3 is 125. So similarly, if we have what did we just say? X equals e to the y. We know that this is our base, e. This is our exponent, and this is our value. So we could rewrite that in logarithmic form. So this is exponential form again. We could rewrite it in logarithmic form as we know our exponent is the answer. So y equals log to the base e of the value x. Okay, so if we go back to our chart here, x equals e to the y, we could write that as y equals log to the base e of x, which means the exact same thing, but we learned earlier that log to the base e, since it's used so often, we call the natural log or the ln. So that we could also say that this blue curve here is y equals the ln of x. So ln of x and log to the base e of x mean the same thing. And it's the inverse of the exponential function. So in general, logarithmic functions are the inverse of corresponding exponential functions. And that's what we have here. And notice that it's only defined for x greater than 0. Okay, so with exponential functions, there's a horizontal asymptote along the x-axis. For logarithmic functions, there's a vertical asymptote along the y-axis. So just kind of keep that in mind. So the inverse of y equals e to the x is found by interchanging x and y. So it gives you x equals e to the y. To find the derivative of y equals ln x, we can use implicit differentiation starting with x equals e to the y. So first we want to recognize that these are two ways of writing the same thing. So if we find the derivative of this one, we're actually finding the derivative of y equals ln x as well, which is what we're interested in doing here. So let's start off with x equals e to the y and derive it implicitly with respect to x. So the derivative of x with respect to x is 1. the derivative of e to the y with respect to x. So we did a little bit of this in the last lesson. So it would be e to the y times the derivative of the exponent, which would be dy by dx. And it's dy by dx, or the slope of the tangent, that we're trying to find. So in order to get dy by dx by itself, we would divide both sides by e to the y. And then we would get dy by dx is 1 over e to the y. Okay, meaning that if y, oh sorry, forgot something here, important, equals 1 over, so if we look at, by definition, e to the y is equal to x. So the slope of the tangent is, or dy by dx is 1 over e to the I, or 1 over x, because x is equal to e to the y. So meaning that if y is equal to the ln of x, or log to the base e of x, then y prime is 1 over x. A very simple derivative again. Okay, we proved it. Very much like the derivative of e to the x's itself is a very simple derivative, simple and beautiful. The derivative of the ln of x is also simple and beautiful. Y prime is 1 over x. Okay? And so I've got that written here for you, but if you apply the chain rule, if we're finding the derivative of the ln of a function of x, then f prime at x is going to be 1 over that function of x, so like the 1 over x, but 1 over that function of x, and that's going to be your outer derivative, multiplied by the derivative of g at x, which is your inner derivative. So for instance, if we want the y equals the ln of, say, 5x, then the derivative, or y prime, is going to be 1 over 5x times the derivative of 5x, which is 5, which is going to simplify to give us 5 over 5x, or 1 over x. Okay? All right, so now we're going to try some examples. So find the derivative. Y equals the ln of 2x. So y equals the ln of 2x. Again, this is a logarithmic function. Y equals log to the base e of 2x. Y prime is going to be 1 over 2x by the chain rule times the derivative of 2x, which is 2. So y prime is going to be 2 over 2x, or 1 over x. F at x equals the ln of x squared. So f prime at x, following the chain rule, is going to be 1 over x squared multiplied by the derivative of x squared, which is 2x. So f prime at x is going to be 2x over x squared. The x in the numerator divides out with one of the x's in the denominator, so it's going to leave you with 2 over x. If you don't see that, think about, you leave the 2, and you're dividing powers with the same base, so you get 2x to the negative 1, because you keep the base and subtract the exponents, which leads to 2 over x. Okay? Y equals the ln of 5. So the ln of 5, there's no x there. So if you find the ln button on your calculator, so here I've got my ln button here, ln of 5 is approximately 1.609, or on this calculator, ln of 5, again, it's the number 1.609437912. It's a number. So this is just a number. Just a number. So it's like saying, what's the derivative of 2, for instance? We know it's 0. So the derivative of the ln of 5 is just 0 because it's a constant. The ln of 5 is a number, it's just a constant. For D, y equals the ln of 7x plus 8 cubed. So it's a ln first, the ln of something that happens to be cubed. So following the chain rule, so this is going to be a ln with a chain rule inside. So first it's 1 over whatever we're taking the ln of, 7x plus 8 cubed. And then we're multiplying that by the derivative of 7x plus 8 cubed, which is 3 times, I'll put this in square brackets here, 3 times 7x plus 8 all squared. But then you have to multiply that by the derivative of what's inside here. So the derivative of 7x plus 8 is 7. And then we want to write that as nicely as possible. So I can multiply the 3 and the 7 and get 21 times 7x plus 8 squared. And then that's over 7x plus 8 cubed. Okay, so that's going to give me, if I'm dividing powers with the same base, so 7x plus 8 to the 2 minus 3 or negative 1, or 21 over 7x plus 8 to the positive 1. And if you can go straight from here to here, that's great. That's preferable. If you need that middle step in there, then do it if it helps you. Okay? All right, y equals the square root of the ln of x. These ones are really important because they also make you realize if you're really understanding all the rules and how to put them together. So this one's not ready to derive yet. I first want to, it's in radical form, I first want to write it in exponential form. So it's the ln of x all to the exponent 1/2. So in this case, it's a chain rule first. So y prime is going to be 1/2 times, it doesn't matter what's in the brackets, so the ln of x to the negative 1/2. And then we've got to multiply that using the chain rule by the derivative of what's inside. So the derivative of the ln of x is 1 over x. And then how do we write that out nicely? So on the numerator I'm going to have 1, in the denominator I'm going to have 2x, but I'm also going to have the ln, I can think about it like this, the ln of x to the positive 1/2. But I would rather write that in radical form. So it'd be 1 over 2x root of the ln of x, because the exponent of 1/2 is the same as a square root. So that's how you would see the answer in the back of the book. So again, this step here would be the calculus step, and then this would be kind of using algebra and radicals, knowing the meaning of exponents, negative exponents, etc., to get it to a more simplified or pretty looking answer. All right, and I've paired this question with right beside it a question that looks similar but is not the same. So here it was the square root of the ln of x, and in F it's the ln of the square root of x. Very different questions. So again, I probably rewrite this as the ln of x to the 1/2. So I'm taking the ln of x to the 1/2. Okay, so this one is first a ln. So to find the derivative, following how to take the derivative of the ln of a function of x, it's 1 over whatever that function of x is, and then you multiply that by the derivative of that function of x, which in our case is going to be 1/2 x to the negative 1/2. So there's our calculus part again, but now we want to write it in a nicer form. So my numerator is going to be 1, and then I've got 2, I've got my x to the 1/2, and then this x to the negative 1/2 is in the numerator. If I bring it down to the denominator, the exponent will be positive. And then I can think about what's happening in the denominator is I'm multiplying x to the 1/2 by itself. So I'm multiplying these powers with the same base. So I keep the base x and add the exponents. 1/2 plus 1/2 is 1. So it works out that f prime at x is actually 1 over 2x, which is a really pretty derivative there. You'll find that a lot of the times in ln questions, the derivative works out to be fairly pretty. All right, on to G. G, we have y equals the ln of x divided by x cubed. So this is going to be a quotient rule. So our first function is the ln of x, and our second function is x cubed. And the derivative of ln of x is 1 over x. And the derivative of x cubed is 3x squared. So we want to use the quotient rule here, which is the derivative of the first times the second. So 1 over x times x cubed, convince yourself that that's just x squared. Okay, 1 over x times x cubed is actually x squared. And then the quotient rule has a subtract sign, so minus the first times the derivative of the second. So I'm going to write that as 3x squared ln of x all over the second, which is x cubed squared. And then we'll just simplify that. So if we look in the numerator here, we've got our two chunks. And they have x squared in common. So if I divide the first chunk, x squared divided by itself is 1, minus 3x squared divided by x squared is 3 ln x, over, and then in the denominator I have a power to an exponent, so I keep the base and multiply the exponents. So then here I'm dividing powers with the same base, so I'm going to get x to the negative 4 times 1 minus 3 ln of x. But I don't want a negative exponent in my answer because I didn't have one in my question. So I'm going to write that as 1 minus 3 ln x over x to the 4th. And again, if you can go straight from here to here, that's fine. All right, so that was using the quotient rule. Again, so we've looked at using power rule, quotient rule, chain rule, all with ln somewhere in it, okay? And this is our unit on derivatives of special functions. So e is a special function and ln is a special function. All right, so our next one is f of x is the ln of x squared plus e to the x. So it's first a ln. We're taking the ln of, in this case, two functions of x that are adding. So f prime at x, so for ln, it's going to be 1 over x squared plus e to the x, and then times the derivative of x squared plus e to the x. So since they're adding, we just take the derivative of them each individually. So the derivative of x squared is 2x, and the derivative of e to the x is e to the x. And then just how that would look in the back of the book, multiply the tops together and the bottoms together. And that would be the answer. You can't divide out the e to the x's because there's addition signs here, okay? So the number in top is 2x plus e to the x, and the number in bottom is x squared plus e to the x. You can't divide out parts of a number, okay? So that would be your final answer. On to I. So y equals the square root of the ln of x squared plus 1. So first I'm going to rewrite that. So it's in brackets, the ln of brackets again, x squared plus 1 all to the half. So I'm changing it from radical form to exponential form. And then if I see something all to an exponent, I know that that's chain rule first. So again, this was just y, so y prime chain rule is going to be a half times the ln of x squared plus 1 to the negative half. So that's the outer derivative. And then we need to multiply that by the inner derivative. So the derivative of the ln of x squared plus 1 is going to be 1 over x squared plus 1. So this is using the how to derive ln, 1 over whatever times the derivative of the denominator, which is 2x. Okay. So then that's the calculus done there. Now we want to make it look as simplified as we can. So I see that in the numerator, if I look, this has got a negative exponent, so it's going to move to the denominator. I've got a 1 and a 1 times a 2x. So in my numerator is going to be 2x for now. We may reduce. In the bottom, I've got x squared plus 1. And then I'm going to move this down to the bottom to become the ln of x squared plus 1 to the positive half. So I can see that the 2's divide out. So in the numerator I've got x. In the denominator I've got my x squared plus 1. And then rather than writing that as an exponential, I'm going to write it as a root, because exponent 1/2 means the root of the ln of x squared plus 1. And that would be as simplified as I can get there for that one. Okay, so moving on to J. I've got f of x equals the ln of x plus e to the x squared all to the 4th. So I see something all to the exponent 4, so I know it's chain rule first. So f prime at x is going to be 4 times, so it doesn't matter what it is, we just repeat it, to the 3rd. But now I want to multiply that by the derivative of what's inside the brackets there. So the derivative of the ln of x is 1 over x. And the derivative of e to the x squared is e to the x squared, and then times the derivative of x squared, which is 2x. So this one we're not going to get to write really all that pretty, because this term here is not going to be all that pretty. But I can clean it up a little bit, so that's all I'm going to want you to do. So within this bracket here, all I would do then is write 1 over x plus 2x e to the x squared here. And that's all you would need to do. Some textbooks might want you to get a common denominator within here of x, but it doesn't help you simplify it really any further. All right, K. K, we've got y equals x to the 8th times the ln of 2x. So we want to think of this as the function of x to the 8th times another function of x, which is the ln of 2x. So there's a product rule there. So we're going to do our first, second function derivative. So my first function is x to the 8th. And my second one is the ln of 2x. So the derivative of x to the 8 is 8x to the 7th. And the derivative of the ln of 2x is 1 over 2x times 2, which is 1 over x. So if I come down here and I use the product rule, y prime is going to be derivative of the first times the second. So 8x to the 7th ln of 2x plus, and then x to the 8th times 1 over x is x to the 7th. So this one ends up being easy to put in factored form because there's a common factor of x to the 7th in both of those chunks. So if I divide the first chunk by x to the 7, I'm going to get 8 times the ln of 2x. And if I divide x to the 7th by itself, I get 1. So there, that one would be in simplified factored form. L, f at x is the ln of x squared minus 1 over 3x. So it's a ln first. So f prime at x is going to be 1 over x squared minus 1 over 3x. So that's how ln works, times the derivative of this. So in order to get the derivative of that, you need to use the quotient rule. So I'm going to come up here. So the first is x squared minus 1, and the second is 3x. The derivative of x squared minus 1 is 2x, and the derivative of 3x is 3. So the derivative of x squared minus 1 over 3x is going to be derivative of the first times the second, so 6x squared, minus the first times the derivative of the second, all over the second squared. So when you have 1 over a fraction, 1 divided by a fraction. So remember, dividing by a fraction is the same as multiplying by the reciprocal. So 1 over x squared minus 1 all over 3x is the same as 3x over x squared minus 1. So I'm going to rewrite this part here as 3x over x squared minus 1. And then I'm going to work on the square bracket. I'm going to expand in the numerator and simplify. So 6x squared minus 3x squared plus 3 over, and then I'm also going to expand in the denominator, 3x times 3x. So 3x all squared is 9x squared. Keep going here. So I have 3x over x squared minus 1 times 3x squared plus 3 over 9x squared. So 6x squared minus 3x squared is 3x squared plus 3 over 9x squared. We're trying to put it in simplified factored form. So I can factor x squared minus 1 to give me x minus 1 times x plus 1. And then within the square bracket, I can common factor 3 out of the numerator. And then, so within the numerator, I can multiply the monomial parts together. So 3x times 3 is 9x times x squared plus 1. And in the bottom, I want the monomial term out front. So I've got a monomial, 9x squared, multiplied by 2 binomials. The 9's divide out. The x takes away the squared on the bottom. So f prime at x in simplified factored form would be x squared plus 1, because x squared plus 1 doesn't factor, over x times x minus 1 times x plus 1. So that's tricky with fractions and exponent rules and factoring. The calculus part was done way back here in the first step. And then everything we did after that to simplify it was algebra. Okay, so we're going to try some applications then. So our first one, our easiest type, determine the slope of the tangent to that curve at the point where x equals 1. So we can see that there's going to be a quotient rule because we're dividing functions of x. So we have the ln of x squared and 3x. If there's no brackets, then you assume that what comes right after the ln is what we call the subject of the ln. So sometimes they'll use brackets and sometimes they won't. Often they'll use brackets that say it was a ln of x squared minus 1. So if there's a binomial, to show you that it's the ln of the whole thing and not just of the first one. And if it's just a monomial, they often don't use brackets, so just something to be aware of. So the derivative of the ln of x squared is 1 over x squared times the derivative of x squared, and that's going to simplify to give us 2 over x. And the derivative of 3x is 3. So it's a quotient rule, so y prime is going to be derivative of the first times the second. So think about that, 2 over x times 3x is going to be 6x over x, which is just 6, okay? Minus the first times the derivative of the second, so minus 3 times the ln of x squared, all over the second, which is 3x squared. So y prime is 6 minus 3 times the ln of x squared over 9, careful with the 9, because 3x times 3x is 9x squared. Okay, so we want the slope of the tangent where x is 1, so we want y prime at 1. So that's 6 minus 3 times the ln of 1, because 1 squared is 1, over 9, because 9 times 1 squared is 9. So this is going to be, now normally I would say like if it was ln 2, leave it as ln 2, but ln of 1 is special. So if you're trying the ln of 1, you should get 0. If I can find my way back to the graph here that we did right at the very beginning. So you can see that when x is 1 in the graph, y is 0. So the point 1, 0 corresponds to the ln of 1 being 0. So that's going to give me 6 minus 0 over 9, or 6/9, which reduces to 2/3. So therefore, m tangent is equal to 2/3. So that's our most common application, again, is to find the slope of a tangent at a certain point. All right, now we're going to apply it to implicit differentiation. So we've got find dy by dx, so find the slope of the tangent implicitly. And our function is x ln y, so we've got x's and y's mixed together, and that's our indication that it's an implicit differentiation question, plus x equals y squared plus 3. So we have to recognize that we have a product rule here. We have x times the ln of y. So our first function is x, derivative is 1. The second function is the ln of y. The derivative is 1 over y, but be careful because we're talking about y. We have to multiply that by dy by dx. So if we're deriving it, we're going to start off with the product rule for that first term there. So we get ln y plus, so x times 1 over y is x over y dy by dx. So that just derived this part here, plus derivative of x is 1 equals the derivative of y squared is 2y dy by dx, and the derivative of 3 is 0. Okay, so there's our derivative. Now we want to get the stuff with dy by dx to one side, so I'm going to subtract this term, leaving me with ln y plus 1 equals 2y dy by dx minus x over y dy by dx. So now on this side, I'm going to common factor out dy by dx. Divide both sides by 2y minus x over y. And then again, not worrying about simplifying, but just getting dy by dx, ln y plus 1 over 2y minus x over y. And 90% of the time when you see this in first year, you're going to be finding it at a point. So at an xy combination, and you'll just be substituting in. So you want to be able to find the derivative and then substitute. All right. So we haven't done one like this since maybe the first chapter. Find the point or points on the curve y equals the ln of 1 plus e to the x where the tangent is parallel to the line. So in other words, they're asking us to find out where on this curve is the slope of the tangent a certain value. So we know the slope of the tangent's involved, so we'll start off finding the slope of the tangent, or an expression, sorry, for the slope of the tangent. So we know y prime is, so this is a ln 1 over 1 plus e to the x times the derivative of 1 plus e to the x, which is e to the x. So we know that y prime is e to the x over 1 plus e to the x. And we want to know where does the slope of the tangent, again this means the slope of the tangent is equal to e to the x over 1 plus e to the x. Where is the slope of the tangent parallel to this line? Well, what is the slope of x minus 2y equals 0? So there's a couple ways to do that. You could do it by putting it into the form y equals mx plus b. So that's going to involve adding 2y to both sides, dividing both sides by 2. So we get y equals, make the slope number jump out in front, a half. Y equals a half x, so m is a half. So in other words, it's asking us where on this curve is the slope of the tangent 1/2? Well, we've got an expression for the slope of the tangent. We want to know where is it a half, so for what value of x is it a half? So we can, some of you might be able to solve by inspection, but we can multiply both sides by the common denominator, which is going to be 2 times 1 plus e to the x. Okay, so the 2's divided on this side and you're left with 1 plus e to the x. And on this side, the 1 plus e to the x is divide out and we're left with 2e to the x. If we subtract e to the x on both sides, we get 2e to the x minus e to the x is e to the x. So this is saying e to some exponent equals 1. We should kind of say to ourselves, we know that that's got to be 0 because e to the exponent 0 equals 1. But we can take the log of both sides, which is what you learned how to do something like that in advanced functions. So log of 1 equals log of e to the x. That's how you solved an exponential equation in advanced functions. Remember the rule, the x comes down. And then if you type in log 1 divided by log e on your calculator, you'll get 0. Okay, so there's only one x value, so that means there's only one point where the slope of the tangent to that curve is a half, but we want to find its corresponding y value, so we go back to the original function, which was y equals ln of 1 plus e to the x. But x is 0, so the ln of 1 plus e to the 0, which is the ln of 1 plus 1, which is the ln of 2. I mean, that's not a nice number. You can try to find it on your calculator, the ln of 2. It's a decimal that 0.6931, etc. So we leave it as a ln of 2. So therefore, the tangent is parallel to the line at the point 0 for x, ln 2 is the y value. Oops. All right, so that was a way more challenging application of finding the derivative of special functions. On day 2, we're going to learn how to derive some more special functions next week. Thanks, guys.